Okay, guys, we left off looking at this curve, and what I explained to you was that this is it's actually a theorem. There actually is this theorem that says that the limit as you can use any as k goes to zero of sine of k over k. The key thing here is this argument, this angle and the denominator has to be the same, is equal to a 1. Because that's the graph. Look at the graph from the left. Look at the graph from the right. But there's a hole there. It's undefined. F of 0 is undefined because obviously k cannot be 0. The denominator cannot be 0. There's a theorem. And we can use that in a variety of ways. The problem I really wanted you to see is this one here. And it looks really strange because t, which is the angle, is going to 0. Obviously, you get a 0 down there. And then if you know anything about sine, or tangent I mean, tangent is sine of t over cosine of t. Let's see, what did that give you? Well, sine of 0 is 0. Cosine of 0 is 1. But this thing goes to 0. So this is an indeterminate form. But maybe we can use that theorem that we just had on the other page if we rewrite this thing. One thing I noticed about your work, when you're working on limits, the limit stays there until you substitute everything in. Since I'm still working on this, I'm going to write the limit. And I'm going to write sine of t over cosine of t and see what happens there. And then secant is 1 over cosine. So I'm going to write 1 over cosine of 2t. Now you might be concerned, what happens when t goes to 0? Well, cosine of 2 times 0 is cosine of 0 is still 1. This fraction is not affected. So I'm still left with that 3t. So when I put my 3t in the problem, so when I put my 3t, that's 1 out of 3t. And I know it looks scary because you end up still having a sine of 0 right here. And now you still have 3 times 0. But look what I can do here. If I pull the 1/3 out, because it's just a constant, and I'm doing the limit as t goes to 0, and I have my sine of t times 1, which is sine of t. And since I pulled out the 1/3, I still have this t right here that can go under here. So I've taken care of this part, and I've taken care of both of those. And what am I left with? I'm left still with this cosine of t and a cosine of 2t in the denominator. Now this is the identity that we just had. Regardless, t is going to 0. This turns into 1. So all I'm left with now is 1/3 times the limit of this piece, which is 1, times the limit of this as t goes to 0. Cosine of 0 is 0. Cosine of 2t is 0. I'm sorry, 1. What did I say? Cosine of 0 is 1. Cosine of 2t is 1. 1 over 1. Final answer is 1/3. And I was using that identity we just had, the sine of t over t. I made it happen. I made it happen. It was magic. Let's look at another one. Show that the non-zero constants, a and b, that the limit as theta goes to 0 of sine of a theta, now that means this goes together, over sine of b theta is a over b. Well, that's real strange. Let me break it apart a little bit so you can see what's happening. Limit as theta is going to 0. And I have a sine of a theta in this numerator over 1. And I have a 1 over sine of b theta. What am I missing in a theta? I'm missing an a theta in the denominator. So why don't I just multiply this fraction by a theta over a theta? All I did is multiply by 1. And how about this b theta? I don't have a b theta on top because even the reciprocal of 1 is still 1. So it's just upside down from the theorem that we had. So multiply by b theta over b theta. So let me rewrite everything to make it look pretty. Limit as theta goes to 0. I'm going to keep the sine of a theta with the a theta times the a theta times, this is my 1 times b theta over sine of b theta, keeping those two together. And what is still in the problem? There's still an extra b theta in the denominator. Now, if you look carefully, this limit goes to 1. What am I left with? A theta times this goes to 1. What am I left with? A b theta in the denominator. What cancels out? Theta over theta equals a over b. So I proved it. Boom, boom, boom. It's been proven. Or people go Q, E, D. It's Latin to say proven. And that's what I wanted to share with you. So here is your quick video for your bell ringer for today. Adios.